There are two kinds of RAM technologies. One is static RAM, SRAM, or dynamic RAM, DRAM. They are quite different in their characteristics and applications. And this table compares and contrasts them. First, they are built differently. SRAM use 4 to 6 transistors to build a single bit, while DRAM uses only a single transistor. Therefore, SRAM is quite more expensive than DRAM. In terms of performance, SRAM is a lot faster than DRAM, and SRAM does not need refresh. DRAM needs a refresh every 10 to 100 milliseconds, otherwise they lose data. Also, DRAM is more sensitive to noises such as EMI and radiation. Therefore, it requires error detection code, which is bad. SRAM is less sensitive to noises and may not need error detection code, which is good. Because of their different characteristics, we use SRAM for cache memories and DRAM for main memories and graphics memory, also known as frame buffer. Let's talk a little bit more about DRAM. So basic DRAM cell has not changed since its invention. And most improvements came from interface logic and fast I/O. The first big improvement was a synchronous DRAM, also known as SDRAM, which used a conventional clock signal instead of asynchronous control. It allows the reuse of the same row addresses as long as multiple consecutive memory addresses reside on the same row address. The second big improvement was double data rate synchronous DRAM, also known as DDR SDRAM, where double edge clocking sends 2 bits per cycle per pin. This is current and modern DRAM technology that we have in our machine. And DDR SDRAMs are distinguished by the size of a prefetch buffer. For example, DDR2 has a 4-bit prefetch buffer, and DDR3 has 8-bit prefetch buffer. Again, this became the standard for most modern computer systems. Let's talk about non-volatile memories. The DRAM and SRAM that we just talked about are volatile memories as they lose value or data without power. In contrast, non-volatile memories retain value even if powered off. Throughout the history, we have different non-volatile technologies. First, the original read-only memory, ROM, is only programmed during production, and next gen, the programmable ROM, PROM, can be programmed once after production. Erasable PROM, EPROM, can be bulk erased using UV light and X-ray. Next gen electrically erasable PROM, EEPROM, has electronic erase capability. We had a breakthrough technology called the flash memory, which is essentially EEPROMs with the partial erase capability. It wears out after a certain number of erasings though. Non-volatile memories are very useful, and we use them in lots of different places such as BIOS, disk controller, network card, etc. Also, the solid-state disk, SSD, has been replacing rotating disk. There's a famous and important trend or problem called CPU memory performance gap. As you can see from the graph, the performance gap between CPU and DRAM or disk has been widening. This is problematic because it means CPU has to wait longer time for memory to respond, and we need a solution to address this fundamental problem. The solution was hinted from the property of a program called locality. the good programs tend to have better locality, which we can take advantage of to bridge this CPU memory performance gap. The principle of locality says that the programs tend to use data and instructions with the addresses near or equal to those they have used recently. There are two types of localities, temporal locality and spatial locality. Temporal locality means that recently referenced items are likely to be referenced again in near future. And spatial locality means that the items with the nearby memory addresses tend to be referenced close together in time. Let's look at an example. We have a simple for loop that iterates over an array and adds up. In terms of data references, array elements are referenced in succession with the stride 1 reference pattern, which is exactly a good spatial locality. A variable sum is referenced in each iteration, which is exactly temporal locality. In terms of instructions, the instructions are referenced in sequence within a loop body. Well, we have to imagine assembly instructions that compiler generates, which is spatial locality, and they cycle through loop repeatedly, which is temporal locality. Now that we know what locality is, we should be able to estimate the locality of a program. For example, this two-nested for loop accesses two-dimensional array A in each iteration, and because the loop variable j moves faster than loop variable I, the memory access pattern for array is not consecutive or adjacent, and therefore it does not have a good spatial locality. We have to swap j and I to have a better spatial locality, and this makes a big performance difference between two versions. Here's the big idea behind memory hierarchy. Memory hierarchy is an intelligent and practical solution for CPU memory performance gap problem, and is motivated by, first, well-written programs tend to exhibit the good locality, and second, the fast storage technologies cost more per byte, have less capacity, and require more power. The memory hierarchy creates an illusion of a large pool of storage that costs as much as the cheap storage near the bottom, but that serves data to programs at the rate of the fast storage near the top.